Hello, we are the CoBruhs, and today we're going to talk to you about CoBruh.
With CoBruh, we set out to create a language with the readability of Python and the type system of C. When you write CoBruh, you'll find that every line is extremely intuitive and self-descriptive. You can write simple Pythonic code with the peace of mind that the types you pass around are accounted for and won't change. While anyone can write CoBruh, we hope that our language will encourage beginners to jump into the exciting world of coding. CoBruh is more than ready to take on simple algorithmic and mathematical programming problems. More importantly, CoBruh prepares you to explore more established languages like C and Java.
You may be wondering, how do I use CoBruh? Lucky for you, it's quite simple. Programs in CoBruh must have a specific structure. They must begin with a mix of global variable and function definitions. These can be followed by a list of statements you'd like to run, similar to those within the main method of a C program. Global variables can be defined like this, and functions can be defined as follows. Now that we're done declaring all of our global variables and functions, we can begin writing the list of statements we would like to actually run. Now that we're done writing our program, we can generate the LLVM IR. And now that we have the IR, we can simply run it.
The CoBruh compiler consists of 4 programs: the scanner, the parser, the semantics checker, and the IR generator. In the scanner, we use OCamlX to write regular expressions to scan the program and generate tokens. We ignore unnecessary code, for example, comments, and we detect indentation because CoBruh uses significant white space. In the parser, we take in the tokens from the scanner, and we use OCamlYak to write context-free grammars to create an abstract syntax tree. This AST consists of more logical blocks of code, for example, assignments, loops, and conditional branching. In the semantics checker, we take in the abstract syntax tree, and we use OCaml to create a semantically checked abstract syntax tree. So we check for scopes, making sure that we know exactly which variable a user is referring to when they call one. We check for types, making sure the user passes in correct types for functions, for assignment, and so on. And we also have other checks. So for example, we have a check for unreachable code. Finally, we have the IR generator, which uses OCaml and the LLVM module. We take the SAST from the semantics checker and we generate LLVM IR code. For example, with assignment, we allocate the correct amount of memory and we put in the correct value.
In order to test CoBruh, we came up with a Python script to automatically run and verify that the current build passes all test cases. So in this file, we go through each file, and if it ends with .error or .out, we take that file and we find its corresponding .bruh file, and we run it. If it's a .error file, we compare to see if the error messages are the same, and if it's a .out file, we compare the output to see if it's the same. Here's the complete loop where we do that. And to run this, we type in the command python3 testall.py, and it runs all the test cases, and as we can see here, it passes all of our test cases.
In order to show off some of the capabilities of CoBruh, I will now solve LeetCode question number 7. This is a simple question in which we are tasked to reverse the digits of an integer. I will begin by defining a function called reverse, which takes in a number n and outputs a number. We begin by setting our result variable to 0. We then loop while the input number is greater than 0. In each iteration of the loop, we do two things. First, we update the result. Next, we update the input number. And lastly, we return our result. Now, we can take in a number from user input, pass it into our function, and then output the result back to the user. Now let's test out our program. Let's input a number like 1, 2, 3, 4, 5, and we should get out 5, 4, 3, 2, 1. And as you can see, the program works exactly as intended.
CoBruh support for arrays also enables us to do dynamic programming problems, like coin change. So with coin change, we're given an array of numbers, which represents the coins that we're able to use, and we're given an amount, which represents the amount that we want to achieve. This method returns the smallest number of coins that we can use to achieve the amount, or it returns -1 if it's impossible to achieve the amount. So to start this problem off, like other dynamic programming problems, I'm going to first define an array. And then I'm going to set every element of this array to some large number. I'm going to set the 0th index to 0 because it takes 0 coins to reach 0 cents. And then I'm going to get into the main dynamic programming logic of this problem. Here I'm going to implement the logic that either returns -1 if we couldn't reach the amount, or returns the number of coins. Okay, so we have this coin change function. Let's test it with one example. So I'm going to pass in the coins, a penny, a nickel, a 6-cent coin, and a 9-cent coin. This is an array of length 4, and we're going to have it reach 11. Now the greedy solution would actually choose 3 coins. It'll choose a 9, and then it'll choose 2 pennies. But our dynamic programming problem actually correctly chooses 2 coins, a 5 coin and a 6 coin. So if we compile this, and then we run it, you can see we choose 2 coins. Perfect.
The 2 main takeaways our team had from this project was that OCaml has a steep learning curve, but once it's mastered, it's amazing. It has many valuable features like pattern matching, which helps you not forget cases, OCamlX and OCamlYak. OCamlX and OCamlYak make it extremely simple to write a high-performance scanner and parser. We also find it fascinating to see concepts from previous classes, specifically CST, coming together to build a fully functional compiler. The best advice for future teams would be to stay on top of things. It's really easy to fall behind with this project, so it's important to set specific goals and try and reach them. Some other helpful advice would be to not be afraid of editing language details. Sometimes you might promise to deliver some really cool features, but later down the line, you might realize that these are unattainable. It is really encouraged to continuously recalibrate and assess what is possible and what is not. For example, you might have already implemented the scanner, parser, and semantics for a certain feature, but the IR generation could be incredibly hard. So instead of continually banging your head against a wall trying to implement this feature, you could recalibrate and modify it or focus on something else. Lastly, it is really important to work as a team. As a team of 3 individuals, seamless teamwork, coordination were crucial to our success. Constant and effective communication allowed us to work optimally. pushing out new features like clockwork. A dysfunctional or uncoordinated team is a recipe for an unfinished product.